Welcome to this explainer. If you're a student of physics, chemistry, or engineering, you've probably stared at a dense textbook at some point and wondered, what fundamentally dictates how energy behaves in our universe? Why does a hot cup of coffee always cool down? Why does a car engine absolutely need an exhaust? Well, today, we're going to demystify the two most crucial concepts in thermodynamics. We're talking about the twin pillars, enthalpy and entropy. So let's dive right in and make sense of these invisible forces that literally shape our physical world.
So, I want you to ask yourself this. What invisible properties govern every single physical reaction around us? I mean, we can easily measure temperature with a standard thermometer, right? And we can measure pressure with a gauge, but what about energy transfer and spontaneity? Figuring out whether a reaction is just going to happen on its own or exactly how much usable heat we can actually extract from a fuel, that requires something a bit deeper. It requires us to look at properties we can't directly hold or see, but that absolutely dictate the rules of the game.
Okay, here's our quick roadmap for today. First, the twin pillars. Second, enthalpy and heat content. Third, entropy and molecular disorder. Fourth, diagramming changes. And finally, number 5, the final showdown. We're going to break all of this down step by step to lower any math anxiety and build a really rock-solid foundation for you.
All right, moving into section 1, the twin pillars of thermodynamics. Enthalpy and entropy are completely foundational. You literally cannot analyze energy interactions, engine cycles, or chemical reactions without them. It helps to think of them as two sides of the exact same cosmic coin. One deals with the total energy available, and the other deals with how that energy gets dispersed.
That brings us to section 2, enthalpy, total heat content. Now, if you've ever felt the sudden warmth of one of those chemical hand warmers on a freezing day, you've actually experienced a change in enthalpy firsthand. But what exactly is it?
Well, here's the precise textbook definition. Enthalpy, which we represent by the capital letter H, is a thermodynamic property that represents the total heat content of a system at constant pressure. I really want you to mentally highlight two phrases here, total heat content and constant pressure. In the real world, most chemical reactions, like just boiling water on your stove, happen at a constant atmospheric pressure. Enthalpy is basically the perfect tool for measuring heat in exactly these types of everyday conditions.
To really grasp its physical meaning, let's think about this quote from our source material. It says enthalpy is the total energy of the system available for doing work other than PV work at constant pressure. So think of enthalpy as a system's bank account of available energy currency. When a system undergoes some kind of process, it has internal energy, sure, but it also has to physically push against the atmosphere just to make room for itself. Enthalpy bundles both of those things, the internal energy and the energy required to exist at a certain pressure and volume, into one really neat package. So the crucial point is how this translates into math. And hey, don't let the equations intimidate you. Let's de-jargon this step by step. The fundamental definition is H equals U plus PV. U is the internal energy, so the microscopic kinetic and potential energy of the molecules. P is pressure, and V is volume. Now, if we're looking at a tiny incremental change in enthalpy, dH, it equals the change in internal energy, du, plus PdV, which is the physical work done by the system expanding, plus VdP. But here is the absolute magic trick of this equation. Remember we said enthalpy is most useful at constant pressure? Well, if pressure doesn't change, then dP is exactly 0. That means that whole VdP term completely vanishes. We are just left with dH equals du plus PdV, which elegantly simplifies to just the heat added to the system at constant pressure, represented as delta Q sub P. It's this brilliant mathematical shortcut that makes our lives as problem solvers so much easier.
All right, let's pivot to section 3, entropy, the molecular disorder. If enthalpy is the energy bank account, entropy is the universe's mandatory transaction fee. It is the fundamental reason you can't build a perpetual motion machine.
Here is our formal definition. Entropy, represented by the capital letter S, is a thermodynamic property that represents the degree of randomness or molecular disorder in a system. So while enthalpy tells us about the sheer quantity of heat, entropy tells us about the quality and the distribution of that energy. Think of a perfectly organized deck of playing cards. If you drop them all over the floor, they scatter, right? They naturally move from a state of low entropy, which is highly organized, to high entropy, which is random and disordered.
Let's dig into the physical meaning. Our source states that entropy is a measure of energy unavailability or the dispersal of energy in a system. And I think that brilliantly illustrates the concept. When energy disperses, like say heat radiating out from a hot car engine into the cold night air, that energy hasn't just disappeared. The first law of thermodynamics guarantees it's still out there. However, it has become fundamentally unavailable to do any useful work for us. Entropy is essentially measuring that lost potential. Like I said, it is the ultimate tax on energy transfer. Let's look at exactly how we calculate this energy tax. The fundamental definition of a small change in entropy, ds, is the reversible heat transfer, that's delta Q rev, divided by the absolute temperature, T. Now, you might be wondering, why divide by temperature? Well, because adding a little bit of heat to a cold, highly ordered system creates a much bigger spike in randomness than adding that exact same heat to a system that's already incredibly hot and chaotic. Now, for an ideal gas undergoing a reversible process, the math expands just a bit, but it follows a very logical path. Delta S equals NCV natural log of T2 over T1 plus NR natural log of V2 over V1. What this equation is actually doing is incredibly cool. It's calculating how the disorder changes due to a change in temperature, that is the first half, and how the disorder changes due to a change in volume, which is the second half. When a gas expands, it occupies more space, which means there are more possible positions for the molecules to be in, which means way more randomness and thus higher entropy.
Let's move to Section 4, Diagramming Thermodynamic Changes. Now, when engineers and physicists analyze complex cycles, like the inside of a refrigerator or a massive jet engine, they don't just stare at a page of equations. They map them out. We are going to build the core concepts of these diagrams entirely in our minds right now.
So we generally rely on two main conceptual canvases. First, I want you to imagine a PV diagram. Picture pressure on the vertical y-axis and specific volume on the horizontal x-axis. If you were to trace a perfectly horizontal line on this conceptual diagram from a state 1 to a state 2, what's happening? You're maintaining a constant pressure. And remember our math shortcut from earlier? At a constant pressure, the change in enthalpy, delta H, is exactly equal to the heat transferred. So understanding the concepts behind a PV diagram is fantastic for visualizing work and enthalpy changes. Now, for our second canvas, picture a TS diagram. Here we have temperature on the vertical axis and our new friend, entropy, on the horizontal axis. If a process moves horizontally on this graph, the temperature is constant. But if it moves perfectly vertically, straight up or down, the entropy is constant. That means the process is perfectly reversible with absolutely no heat transfer. And here's the really powerful part. If you conceptualize the area underneath a curve on a TS diagram, that area actually represents the total heat transfer in a reversible process. These two conceptual frameworks, mapping pressure against volume and temperature against entropy, are the twin lenses through which we decode almost any thermodynamic mystery.
Okay, we've made it to Section 5, the final showdown, enthalpy versus entropy. Let's put these two titans side by side to really lock in your understanding of the source material.
Here is your simple final summary. In one corner, we have enthalpy. It is the total heat content of the system. Its primary domain, processes at a constant pressure. It basically tells you exactly how much thermal energy is moving around. In the other corner, we have entropy. It is the measure of randomness or energy dispersal. Its primary domain, determining spontaneity. It tells you the direction a process will naturally flow and whether that energy can actually be harnessed to do something useful. If enthalpy is the currency, entropy is the inflation rate.
And look, despite their contrasting natures, both of these properties are absolutely essential. You need enthalpy to know if a chemical reaction is going to release enough heat to, say, power a massive turbine. But you absolutely need entropy to know exactly how much of that heat is doomed to be wasted as exhaust. Together, they form the complete, undeniable foundation for analyzing energy interactions and process behavior in the real world. So, I want to leave you with this provocative thought. The next time you watch a simple cube of ice melt in a glass of water, or you see a car speeding down the highway, try to look past the obvious. Knowing how heat content and energy dispersal govern literally everything we do, how will these invisible properties, enthalpy and entropy, dictate the very next physical reaction you observe? The fundamental rules of the universe are happening right in front of you, every single second, if you just know how to measure them. Thank you so much for joining me for this explainer. Keep asking those big questions and keep learning.